Hey guys, I recently posted a video about Morse code from my engineering analysis and computation class, which is basically just C programming with that little MSP430 Launchpad from Texas Instruments. So, I wanted to give you guys some context if you ever decide to take this class, or if you just want to have a TI Launchpad, you know? So, first things first, let me show you how I got it done. So, the very first thing I did was I got the Launchpad. It's $20 on the Texas Instruments website, and I think I've seen it go down as low as $13. You might see like sales that go down to like $7, but that's like an old version. Like, the $13 version has like these soldered female pins on it as well, on the bottom. Now, once you get the Launchpad, you want to get something called Code Composer Studio. That's personally what I used. There's also Energia, which is the Arduino version for Texas Instruments. And if you want to get it, all you need to do is go to Texas Instruments website. Like, all you need to do is like go to ti.com Launchpad, and when you're on here, you just go to Software, select your IDE, and bam, Energia CCS Cloud Code Composer Studio. I use this. CCS Cloud, I have no idea what it's about, but I heard that Energia is the Arduino version. So once you have Code Composer Studio, you open it up and you'll get something like this. Now, what you want to do, first of all, is download all the versions with the MSP430G2 model. Now, you'll see things like G2553 or G2452, and you don't have to worry about those. Those are just the chips that you put on it. The whole entire board itself is the MSP430G2. The microcontrollers are the G2553 and the G2452, or whatever that numbering is. And as you can see, I used the G2553 chip for this one. I'm gonna copy and paste this in a paste bin, and I'll just put it in the description. So to make sure it works, you want to go to Properties, and you want to make sure the variant, first of all, is your MSP430 specific chip. You can go here and type it down. G2, and maybe if you're using 553, bam, it's there. Or if you're using 452, it's there. And the reason why I'm listing these two specific chips is because, well, they're the ones that come with the board. The 553 is the one that's put in the board by default. And the reason why I'd say is because it has more memory in general, both hardware and RAM. And then you want to make sure it's connected properly, because there's something called COM ports, and you can tell by simply going to Device Manager. I just right click the Start menu thing, and bam. And there should be something called ports. See the COM, and that's where your MSP430 is going to be. Now, if you're finding problems with connecting it, what you can do is you can go to these port settings by just right-clicking, going to the properties, and then you can go to advanced. Yeah, right there. And well, here you go. You can change your COM port. Now I think what's listed is 1 to 4 inside Code Composer Studio, so that's the ones you want to be messing with. And once it's connected, you can identify it, make sure it works. And yeah. If you have problems with this, I'll figure it out and give you some help later on. But for now, here's some context on everything I'm doing. Okay. The reason why I'm doing this, by the way, is because when I searched on YouTube all these things, people just post their projects, but they don't really explain it, you know. And the reason being is because when you're making these projects and like posting them, it's usually just for a class. Like that's what I did, and like nobody really wants to put in the explanations, because all the explanations is what they learned in class. But maybe you just want to learn it on your own, and that's what I'm here for. So first of all, know that this is in C, not C++, C, raw C, and that means you need to have a good, very strong knowledge in C. Like, engineering, analysis, and computation is known as the C class. Just C, programming class. Like an intro to C class, but with this microcontroller at the very end of the class. Like, 95% of what you learn is just C programming. So that's how important the knowledge of C is for this. So, first things first, there's the header file. Like, usually what you work with in the class is stdio, because you're using computers and stuff with standard inputs and outputs. But in this case, we're using the Launchpad, so we need to make the header for the Launchpad. And as you can see, I defined a constant called size, and this is basically the size, the maximum size of this string right here. And the reason why I put a string up here is because the Launchpad itself doesn't have easy input and outputs. Or rather, it does have outputs. It has the LEDs, obviously. That's how I'm even making the Morse code at all. But the inputs, like, it's not that easy to plug in a keyboard to it. Like, if you wanted to, maybe you'd have to put a booster pack that costs like $10 or more, and well, maybe you don't want to do that because it's a $20 investment or a $13 investment. So that's why I put the string up here. And if you notice, it's chicken crossing. That's actually the message I put in the Morse code video. And I also made a function called read. And as you can see, I said the J acts as the index, which is a variable used to travel across an array, if you didn't know. I also assigned another index called I, and this will be for the delay timer. There should be a function in the header that allows you to specifically set up times. Like, I think it's sleep. But in our class, we just used a for loop, and that's why I assigned a I counter. I call it an index. It's not an index, actually. It's a counter. Screwed that up. But yeah, that's what it does. Now, here's the main function, right here, which is the main bulk of it, as you could imagine. And it has a special something right here. This is called the Watchdog Timer. And what this command does is it pretty much puts a hold on it. The Watchdog Timer, what it does is it makes sure that the program isn't just randomly looping over and over and over and over again. Because maybe if it does that, then a problem is going on. But in this case, we do want random loops, because that's what this whole entire delay is. Now if you use the sleep function, maybe you don't need it. But in this case, I used a for loop, because that's what the class taught me. But what you'll also notice is something funky right here, like this this little bar equal sign. What this means is or together with or the direction, the P1 direction, together with this. So it's kind of like the A plus equals, or maybe minus equals B, and which is pretty much equivalent to A equals A plus B. And what it's basically doing is it's ORing these things together. Now, if you don't know what that is, it's a very vital concept here. So I'll, right here. Yeah, much larger. When you OR things together, you're basically making a logical statement, like based on true and false values. But in electronics world, it's binaries 1 and 0. So if you think of 0 as false and 1 as true, and you have a little bit of knowledge in a discrete, then it's kind of easy to think about. But if you don't, well, that's what I'm here for. So in discrete, it's good to think of these things, not and, or, XOR, quite literally. Now, let's start with and. Because not, it's actually not used in my Morse code at all. So I'll ignore that for now. But basically what it's doing is it's saying if it's not A, then it's pretty much the opposite of what A is. So if it's not false, it's true, right? If it's not true, it's false. Simple as that. Now, and it's using two things. Now, what you want to do is think of it like, what would make the conclusion true? If you're saying A and B need to happen simultaneously, then the only way the conclusion can be true is if they do happen simultaneously. So it's like you're saying, if you want to watch a chicken cross the road, you need to have a chicken crossing the road, and you need to be watching it. Well, if there's a chicken crossing the road, but you're not watching it, then obviously you didn't see the chicken cross the road. Now, if you were watching the chicken, but it didn't even cross the road, then you obviously didn't watch the chicken cross the road. And if there's no chicken, and you weren't watching it, then yeah, you definitely didn't see it, because it just never happened. And you weren't even paying attention. And that's what these things are representing. If you just think of A as probably the chicken crossing the road, the B as you watching it, nope, nope, and nope. Not watching it. Wait, that was B, right? Well, whatever. If you didn't watch it, and it did cross the road, well, you still didn't watch it cross the road. If you did watch it, but it didn't cross the road, well, you didn't watch it cross the road. But if you did watch it, and it did cross the road, then, yep, you watched it cross the road. Simple as that. Now, OR is, OR is basically saying that there's a couple options. There's a whole bunch of options you got to get something done. Okay? You could do this, or you could do this to get the conclusion done. You could, if you're hungry, for example, and you could fill your stomach by eating pizza or fried chicken. Then, if you eat the pizza, well, you're not hungry anymore. If you eat the fried chicken, you're not hungry anymore. If you eat both, you're definitely not hungry anymore, right? It's not like 2 times, which is why it's still 1. It's just you're not hungry anymore. But if you didn't do either, well, you're still hungry. It means you're just starving yourself. So that's what exactly this means. A, if you didn't eat the pizza, if you didn't eat the chicken, then you're still hungry. A, if you didn't eat the pizza, but you did eat the chicken, then you're not hungry. And it keeps on going, because if you eat at least one of these things, then you're not going to be hungry anymore. Right? So that's why the only time it's false is when nothing happens. Like you didn't eat anything. You're hungry. Now, in reality though, whenever we use the word OR, like in a conversation, we actually don't think of the logical OR, surprisingly. We're usually talking about exclusive OR. Now, what exclusive OR is basically saying is that it is OR, but there's a restriction in that if you did both simultaneously, then there would be problems. And the problems would make the conclusion false. Like, for example, if your parents allowed you to get a piece of candy, okay? One piece of candy out of 2 things. If you didn't ask for it, then they're not gonna give you the candy, right? That's why A and B, like if you didn't choose any of the candy, they're not gonna give you the candy. So that's why this is false. If you ask for B, like the second piece of candy, then yeah, they'll give you the candy. If you ask for the first piece of candy, yeah, they'll give you the candy. But if you ask for both of the candies, they're gonna be like, no, you can't have both. I'm not spending all this money for you. You can only choose one candy. Nuh-uh. False. They won't let you have the candy, because they don't want to invest all that money on you. That's exactly what XOR means. And yeah, that's pretty much what you think of when you're using OR, because usually when people say you can do this or you can do this, well, it kind of implies that, well, you can't do both, because they wouldn't be using OR. Like, you can do this or this and this. That's usually what they would say. Now, these three operators are very important here, and I'll show you exactly why. Right here, what I'm doing is I'm ORing 8 bits with 8 bits. And if you don't think this is 8 bits, then it probably makes sense, because it's only like 2 numbers with like a random 0x in front of it. Like, what does this even mean? It's just like 4 things. Well, actually, it's just 2 things, because what the first what the 0x in front of it stands for is hexadecimal. Now, as you know, all the stuff in computers mainly uses binary. Recently, it's been evolving to try and use quantum stuff, but that's a whole other story. Like, whoa, no, quantum, please stop it. So for now, we're just thinking of binary. So here's the general gist of how it works. There are pins on the Launchpad, okay? And even though the pins don't look like they're assigned to anything, and even though the pins, I might have thrown that little booster pack on, which is that like circle thing. You don't need that, by the way, for this project, as you can see, because one of my videos didn't even have it on. These pins are assigned to certain things on the Launchpad. Bit 0 and bit 6 are assigned to the LEDs. There are 2 LEDs, a green one and a red one. The red one is the first LED, and the green one is the second LED. So, the way this works in binary is that it always starts at 0, okay? So, if you're talking about the first pin, you're actually talking about pin 0. And then it goes to like 0, 1, 2, 3, 4, 5, 6, and then 7. And it just stops at 7. Doesn't even go to 8. Because if you add 1 to 7 with 0, well, that's 8 right there. In this case, they're actually called bit with a capital. So, if you actually just use bit 0 and bit 6, you can do the same exact effect. But in general, using hexadecimal will be useful for if you're working on projects like some coding software where they don't have assigned names, because what this bit 0 is conveniently assigned to inside this header file for the MSP430G2, and yes, just G2, because it's the same for both 553 and 452, is 0x00 0, 1, which basically means hexadecimal 1. Now, you could just literally erase all these 4 more zeros, and it's literally exactly the same. Just, it's 1. Throw any zeros in front of it, it's literally exactly the same. As long as you have these two to indicate that it's hexadecimal. Bit 6, I'm using capital because that's actually how it needs to be shown if you want to represent it, is assigned to 0, 0, 4, 0. And that is 6, even though it's 4. How strange is that? Well, here is the logic behind it. So you can use it for maybe if you're doing other things, like programming in other languages that don't conveniently show this. So binary only has 0 and 1, right? Which means it is base 2. It has only 2 options, 2, 0, and 1. Hexadecimal is known as having 0 to 9, and it has A to F, which is A, B, C, D, E, F. 1, 2, 3, 4, 5, 6. Which is why it's called hexadecimal, because it has 6 letters, and it has 10 decimals. So, what it means is it's base 16. And the fancy way that we make it easy to translate binary to hexadecimal is we notice a certain trend, okay? We notice that 2 times 2 times 2 times 2 is what? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. And that is how we make it easy. So, how many bits were there again? Oh, that's right. There were 8 bits, right? And that means that what you can do is you can separate it into 4 binaries on each side. And each binary, each like 4 sets, will be able to be read to a particular hexadecimal. Because if these 4 binaries will equal 16, you can represent one character in hexadecimal with 4 binary numbers. And if you don't know how to count in a binary, I'll show you just a second. So let's say we have maybe this value and maybe this value, okay? So in decimal, we go from 0 to 9. And once we reach 9 and add another 1, we go back to 0. But we add 1 to the next line, right? And the way we read it is that, well, that's 10, right? The 1 on the end and the 0 is just 10. Now if you added 1, then the one, the second one would be 10, and the first one is just 1. So 10 plus 1 is 11, right? Well, in this case, each of these things are just 2, right? They're just known as 2 values. So it goes 0 to 1, and then resets back to 0. But as you know, when you go to the third one in decimal, it's 100. The fourth one is 1,000. And what is that? It's 10 times 10 times 10. Right? So, in this case, what you do is you do 2 times 2 times 2. So, what this actually is represented as is, this first one would be a multiplier of 1, because it's like 2 to the 0th power, and everything to the 0th power is 1. Because when you multiply everything in the first line by 1, it's just the first thing. But once you finally reach the next level, that's 2, because you can't reach this without passing through all the levels of the former, right? But also on that notion, you can't pass through this one if you haven't passed through all these. So you would multiply that by 2 again, which would make it 4. And again, which would make it 8. And again, which would make it 16. And 32. And 64. And 128. Now, it would be a real dang pain to multiply by all these big numbers, right? Like 128 times 0, 64 times this one, and like try to add the 64 with all these things, right? But that's exactly what the hexadecimal is for. What you can do is you can just ignore these former ones and just work with these 4 things. Multiplier of 1, 2, 4, and 8. And the reason why is because the value you get from this will become the hexadecimal digit. Okay? So, here's what you do. There's a 1 at the very end, and that is assigned to 8. So you consider this an 8. There's a 1 as the second one, that's a 2. So what you do is 8 times 1 plus 2 times 1. 8 plus 2 is 10, right? Now, this 10 is actually a hexadecimal digit, okay? And as you know, 10 is not a decimal number, because it goes, well, 10 can't be one digit in a decimal number, because it only goes from 0 to 9, right? So, in this case, it starts going into the letters, because right after the numbers will be the letters. And this is actually the easiest way to tell the hexadecimal. Like, all you need to know is that 10 is A. And it becomes a lot easier from there. So, what you do is that this first character is A, and this one, this is the third number, which is 4, and since it's just a decimal, you would call it 4, because that's what it is. And then, this binary representation is this in hexadecimal. These things are literally exactly the same. How neat. And that's exactly what this is doing right here. This is 41. So this is actually what the 4 is, because we calculated it. And the 1 would just be, instead of this, it would just be this. And guess what? LED 0, no, LED 1 and LED 2, right? Because they're assigned to pin 0 and pin 6. 1, 2, 3, 4, 5, 6. Oh wait, I messed that up. It starts at 0. That's why, right? 0, then 1, then 2, then 3, then 4, then 5, then 6. Yeah, you always have to remember that inside most of these computer things, numbering systems typically start at 0. They don't just start at 1. And the reason being is that, for one, it saves a lot of, well, let's just say it's allows you to extend your options. Like, if we started at 1 in decimal, you would be missing a whole entire digit. Like, it would be 9 instead of 10 digits. And you don't want that happening. Like, you want to have 10 things for one character. So things typically start at 0, and this is one of those things. Pins, bits, bit assignments, and stuff like that. So what this operation is referred to as is bitwise operation. This bar is known as the OR bitwise operator. And if you actually go to your calculator, you can actually see it. All you need to do is go to the programmer and bam, OR, right? So if we do binary, and no, actually let's do let's do hexadecimal. So let's say we have just a 0, okay? And we want to OR this with a 41 in hexadecimal. So we just do 41 OR with the 0, right? What does that get? Well, 41, right? And fortunately, it shows you this binary representation right here. It's the exact same as what I showed right here, if you notice. Right? At 41, right there, right there. But if you do an OR with maybe to do a binary OR with 1, 0, what you'll see is that this 1 just popped into here, right? And this other one just stayed the same, right? And what basically happened is that the 10, like the 10 that I put in, let me just write it up here to make it clear. The 10 that I put in looked like this. Okay? And then we ORed it together using what? Using the truth table right here. Whoa. And guess what? 0 and 1 is what? 1, right? So, that ended up being a 1. 1 and 0. 1, not and. I keep on using and. 1 or 0 is 1, right? 0 or 0 is 0. So, because these two are zeros, that's just 2 zeros. More zeros, more zeros. And then 1 or 0, that's a 1. And another double zeros. Guess what? Hey look, that's exactly the same as the result that was gotten by the calculator. And this is why it's called bitwise operators, because what you're doing is what? You're looking at each individual bit. And then you are comparing them and seeing what the conclusion is. Like, if you do this or this, what is the conclusion? Well, it's this. It is this value. And if you convert it to hexadecimal, you'll get that. And let's verify it, huh? What is this? The second digit? That's 2. What is this? The first digit? That's 1. 2 plus 1, that's 3. What is this? It is still the third digit, which is 4. That is why it's 43. Pretty fancy, right? And the reason why we do this here is because the P1 direction, which is what P1 dir means, port 1 direction, as you can see, it is a registry for the outputs and inputs for these pins. It tells you, is that pin, like, is the bit 0 pin, the pin 1, the pin 0, is the pin 6 input or an output? And those are two values, right? And guess what? We're talking in binary. Even though we're showing this in hexadecimal, this can be converted to binary and shown in binary. So the 0 means input. 1 means output. So the reason why we're ORing these together is because we want to make these pins outputs. Because as you can see in here, when we ORed the 10, it seemed like a 1 was added here. In fact, if you notice, right here, it does use the plus symbol, right? And you'll commonly see in logical Boolean algebra that OR is referred with a plus sign, and as well with the ampersand, which is also known as the and sign, right? XOR will be referred to this also if you're using operators. If you're in discrete, what you might see is you know what, let me open up Word just to show you exactly what it is. In discrete, what you will see is operators right here, binary operators, right? what you will see in discrete is that this this upside down V is AND. This V is OR. See? Logical OR, logical AND. While this here, this circled plus, is XOR. But that's in discrete. If you learned it, but you haven't taken this class, it's a good way to figure out how it connects together. So, once we do that, we want to initialize these. I wanted to initialize these LEDs to 0 to make sure that nothing was wrong. Now, what I mean by nothing was wrong is in the Morse code video, I didn't use LED 0. I didn't use LED 2, which is the green LED. But this time, I decided to use it just to check for errors. And basically what's supposed to happen is that at the very end, it should be green. Like the green LED should be on. But if it's blinking while it's on, while the green LED is on, the red LED is blinking, that means there's a problem. It's very useful for whatchamacallit, figuring out if there's bugs in your code. So what I did here was I used an AND operator, and if you see here, it's actually B and E. It's like, whoa, you're using pretty large hexadecimal, because like the letters, they're like beyond 10. Like B is 11 and E is A, B, C, D, E, which is 15. Wait, no. A, 10, B, 11, C, 12, D, 14, E. Yeah, it's damn. Right? But let's see here. I kind of had a brain fart. Blah. Anyways, I'll write these B's and E's down just to exemplify it. So 10 would be 8 and 2, right? But this is B, so it's actually 11. So it's 8, 2, and 1, which is the fourth bit, the second one, the first one. And then we have the E, which is 8, 4, which is 8, 9, 10, 11, 12, 13, 14. I still feel like there's a problem. I think E is 14. Let me check this out. Hexadecimal. Actually, no. I can just use a calculator, right? Yeah, it has an E. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, it is 14. I don't know how I derped so hard there. So where did I put it? Right there. Okay. So yeah, this is E is 14. So this is what it would look like. Okay? Now if you notice right here, I'll just copy and paste it. I'll just copy and paste this to make it a little bit more clear. You might be able to see the reason why I use this number in particular. If you notice, This and this is literally the inverse of each other. Every single time there's a 1 here, there's a 0 here. Every time there's a 0 here, there's a 1 here. So I basically just kind of flipped it around. And the reason why I flipped it around is because if you look at the AND table, if you AND a 0 together, then it will become 0. It'll force it to become 0. But if you AND a 1 together, it'll just stay as the 1, right? And here we go. I'll show you right here what happens. So if we AND this, if we so if you AND these two values together, assuming that this is the original number. You know what? I'm going to change this number. Just like this. But even so, what you should notice is that if you AND these two numbers together, these two binary numbers, you should get this as the result. And here's the reason why. If we look at the AND truth table, 0 and 1 makes 0. 1 and 0 makes 0. And 1 and 1, right here, will make the 1s. Which is why this is 0, this is 0. In fact, the only time the result will become 1 for the conclusion is when they're both 1 simultaneously, right? Because this and this must occur in order to get the conclusion. So let's see if this is the case, huh? So if we just do 1, 0, 1, 1, 1, 1, 1, 0, which is the first, ANDed with the original, because this is supposed to represent bit 0 being 0, bit 6 being 0, while the rest are just 1s. And this original is 1, 0, 1, 1, 0, 1, 1, 1. And the original could be any case. But let's just do this case. And let's see. Yep, the result is exactly the same. Right? Right here. This, this. Exactly the same. Now, a trend you will notice is that I'm not sure if you'll actually notice it, or if you have or not, but it's very important. Okay. Let me back up here, okay? So I'm talking about all of these operators, okay? I'm talking about AND, talking about OR, talking about XOR, exclusive OR, to be more specific. But why? Why do you even use this? Because if you think about it, if all you need to do is to have the output being 1 or 0, like to alternate it whenever you want to get the result you want. Because in this case, we want the LED to blink, right? So if we turn it to an output, it will output a light. But if we turn it into an input, well, there's nothing to it's going to input something, but since the input does nothing, well, all that happens is that the light turns off and nothing else happens. So if that's all we need to do, then why don't we just go up here and set it equal, right? Why don't we just initialize it every single time we want to? Like, why don't we just initialize right here? Like this, set it equal to 0, not 0, bit 6 to be exact. This is bit 6 because this is hexadecimal 4, and that would be hexadecimal 40, and that would be right here. Hexadecimal 40, which is, guess what? Bit 6. 0, 1, 2, 3, 4, 5, 6. Right? So, why don't we just set it equal to it? Like, can't you just do that? Well, yeah. Yeah, you can. But, there's a big problem. You see, it works if you're doing only one thing. But guess what? When you're not doing just one project like this, and you have many projects that's happening simultaneously, the pins are actually being used for multiple projects instead of just this alone. Because yes, that can happen. You can have multiple functions, multiple projects, in other words, to be based on the same variables. And these variables being, well, these pins, right? If that happens, and you just initialize it like that, then you're gonna pretty much screw up every other function. And you know, I heard somewhere that things like cars use 25 of these microcontrollers. And if you think of it that way, and how much these microcontrollers like manage the stuff that happens in cars, or like other things, like maybe planes. Because yes, planes have a lot of microcontrollers in it. Then you're gonna sabotage pretty much all the work people make just by initializing like this. Because this means that right here, if we simply set this BE, okay, this hexadecimal BE equal instead of doing this AND, what will occur in this calculation right here, where we had this as the original and we ANDed with this, instead the conclusion, instead of being this right here, it would be literally this, right? 1 0 1 1 1 1 1 0, right? Yeah, that can work. But then you have to look at all the changes that occurred because of doing this. You unnecessarily changed bit 0 1 2 3. You see this, like this was unnecessarily changed, like maybe 3 was supposed to be a output to like power maybe, but oh snap, you set it to input. So now it's supposed to, it's saying, oh, I need to get power, but oh snap, I guess we just took away the power from the other guy. And if you do that, there's going to be a huge problem, you know? Actually, no, this is supposed to be the original, so in this case, the example would be this is inputting power, right? This is supposed to be inputting power into this. But if this is outputting, maybe just the device doesn't even work at all. You know, this pin 3 might have that purpose. I'm not sure exactly what pin 3 does on the MSP430, but who knows? What if it did happen and you just changed it? Well, you're screwed, right? It's a bug. Like, oh snap, something isn't turning on. Why isn't it turning on? Oh, it's because we did an equal sign. That's why. And this is the big reason why we use these operators at all. And to give some context, here's the trends that actually happens. So if you AND any binary digit with 1, you'll get the same binary digit. Because originally, this is what it looked like. Okay? And this is the original. Think of this as B. And this. And in this particular bit, let's just think of it as 1, right? B and 1. Well, 0 just became 0, right? Which is the same as B. And if we do another example, let's say right here. Right here, right? This is 1, which is B. And this is 1. Like, it's literally the same, right? This is 0, this is 1, this is 1, this is 1. But this all came from B. So, this is 1, this is 1. Guess what? It became 1, which is the same as B. So it's B. Like, regardless of if it's 0 or 1, the answer will be the same exact value that it was before. 0 will become 0, and 1 will become 1. But when we AND a 0 with any binary number, we will get 0 as a result. So, as you can see here, this is the original, and this is the 0. And guess what the answer is? Even though this was a 1 before, it became 0. And here's another case. It's a 0. It was originally a 0, and we ANDed it with a 0, and it became 0 still. So regardless of if B was 0 or 1, the result was always 0. And this is a very important trend. And it's the main way we manipulate these bits without sabotaging everything that we worked for. And you can notice these trends by actually looking at this truth table here. All you need to do is think of this A as 0 right here. Because if you notice, this B is 0, 1, 0, 1. So it's like the same here and here. But this is always 0 up here. This is always 1 down here. So if you split it in half and consider A as 0, then you can see that the result is always 0 regardless of what B is. Which means that right here, 0 ANDed with B, A ANDed with B is 0 regardless. But right here, if you AND an A, and A as 1 with B, regardless of what it is, it will stay that way, because 0 becomes 0, 1 becomes 1 from B. So, if you AND 1 with any binary number, it will become that binary number. And the same can be seen with the OR operator. If you OR a 0 with the B, you will get the same exact values for the B. So there will be no change in the B, which is why it's B. 0 or B is B. But if you do 1 in B, 0 or 1, it will always become 1, which is here. And now finally for the XOR operator. This is known as the toggle operator for what you will see very soon. 0 and 0. Like 0 as A, XOR with B. What's that? Well, as you can see, just like with the OR, there's no change. Like, B will stay the same. But, if you do 1 XOR with B, you'll see that, 0 from the B became 1 in the conclusion. But 1 as B became 0 as a conclusion. Does this kind of seem familiar? I wonder, huh? Yeah. Inverted B. That's what it is. And yes, I said the word inverted because, well, this says not here. The actual gate itself, which is what these things are actual physical objects that people use. They're called gates. AND gates, OR gates, XOR gates. This is not called a NOT gate. It's called an inverter. And it is typically shown with this tilde, like squiggly thing, or a apostrophe, or a overbar. Let me show you up here. Let's say B as an overbar. Should be here somewhere. Accent, yeah, there we go. This overbar up here, like this, is also considered not B, inverted B. And there's another fancy operator. Let me see. Binary, relational. Advanced relational. Okay, I'll just draw it in paint. Basically, it looks like this. This little, kind of wedge. I don't know what you'd call that. The wedge is actually usually called like this, but which is and. Yeah, that's the logical and, actually. But yeah, that symbol is usually depicted as knots. There's a whole bunch of versions to say not or inverted. It just depends on what the program wants. And in this case, if you wanted to use it here, if I'm not mistaken, you would be required to use the tilde, which is pretty much the symbol. If you press the button, the key to the left of the number 1 on your keyboard. Like you have to shift, click that button. Yeah. But fortunately, we don't have to use the inverter for this Morse code. All you need to know is that these things are really important. And why? Because, very simple, okay? Now, if you look here, initialize LED 1 and 2 to 0. You know how we do that? Well, looky here. These relations. Which one transforms it to 0, but keeps the other the same? Oh. The AND. Oh. And. That's why you use it. For the transformation of the whatchamacallits. Oh, I actually don't use a toggle. Well, okay. I wonder if I have a blink somewhere. I'm going to show you my blink code, just to show you where I used XOR. Right here. There we go. Right here. As you can see, what this is doing is it's toggling the LEDs every time this happens. Every time this condition happens, the counter, the first counter, is activated. The I will become 0, and the output will toggle, like the bit of LED 1, which is 0, bit 0, will be toggled. As you can see, it says LED 1 right here, but if I'm not mistaken, yes, right here, they actually use this LED 1 as a constant. Like, this is how you make things a bit more clear in your code. Like, what you can do is you can define with this preprocessor directive noted by the hashtag thingy a certain word, a certain thing as a value. In this case, it's bit 0. Bit 0 is known in the header by the same exact thing as that right there, the 0x0001, which is the hexadecimal 1. And LED 2 is mapped to bit 6, which should be, I don't know why it's saying this, but it's basically mapping to hexadecimal 40. And the reason why you'd use a toggle is because, well, you want it to turn on and off and on and off and on and off and on and off. That's toggling, right? Turn on, turn off, turn on, turn off. You do one thing to just turn it on and off. You're not flipping it up, you're not flipping it down. Like, you're not just flipping it up and down, you're just doing one thing at a time. And that's what makes the XOR operator useful? In this case, I decided against it to have more control over how long I whatchamacallit, how long the lights stay on. So I just define them rigidly with the OR. It's on right now. It's off right now, right? It's on right now. It's off right now. It's on right now. It's off right now. I could have toggled, but I decided against it. Like, literally, this will achieve the same exact result. If I did this operator, like this little change right here, will achieve the same exact result. Because basically what's happening is I'm setting it as 1, but instead of ANDing all those 1 values within the 0 as the bit 0, like the hexadecimal FE I had before, instead this would toggle the first bit 0. It would toggle bit 0. And since it was 1, well, it'll go to 0. So literally, this would achieve the same exact result. No problem. And heck, I will keep it there just to prove it. Now, here is the main bulk of it. Okay? Now that I've explained the operators, which I used a lot of time for, but it is literally one of the most important things for this. Here's the context, okay? P1 direction is a register. If you don't know what a register is, a register is it's a very important circuit for sequential circuits. It's a very important part of sequential circuits, which is basically using save states and loading from these states. What we're basically doing is we're saving it to a state called the P1 direction, like a register. That's what we're saving it to, the register of the P1 direction. And to change it, we're using another register called the P1 out. And we're strictly using this to make sure that this program knows that it's using this, it saved it to rigidly place it there so we can access it freely, and so that like any other program can change its change that rigid state to a different set of bits. Like for example, if I only set it like this, like 0, 1, and I said that, well, I'm only using bit 0 because this is hexadecimal 1. Then, even if I had this, the LED for the LED 2 will not be affected because this register is only assigned to the bit 1, the bit 0, which is LED 1. But by doing 41, hexadecimal 41, I state clearly I am using bit 6 and bit 0. That allows me to use this. And in fact, in my code for the Morse code video that I made, I actually did use 01. And I changed it recently to 41 to add this LED2 aspect to it. And the LED2 is just for this error checking right here. Like, yeah, this is supposed to be an OR. I think I changed it for a demonstration. But right here, what's supposed to happen is that the second LED is supposed to turn on after the Morse code is finished. If the green LED, which is LED2, is on, and LED1, the red LED, is still blinking, then there's a problem, because that's not supposed to happen. And in that case, basically what would happen is, like, there would be a minus sign, or a parenthesis, or a comma. Like, if you look right here, these read characters, okay? A lowercase, A uppercase, the 0, which is actually the decimals as a character instead of as a number, and even a space character. But it doesn't do special characters. So if I threw in a special character, that would be an error. And that's what I am trying to express right here. So what I'm doing is I set the registry to show that I'm using LED 1 and 2 by showing hexadecimal 41, which declares LED 1 and 2, which is bit 0 and 6 as 1 outputs. So it's showing that these are the outputs I'm using. Right here in P1 out, by using P1 output, this is what it's doing, okay? There's obviously something else called P1 in, right? But P1 out is basically stating it's only affecting outputs. Not gonna be affecting the inputs in the P1 direction. So by doing this, I AND together the B and E, which is representing the bit 6 and bit 0 as zeros, and it's ANDing it with that value, which is basically BE. See, bit 6 is 0, and bit 0 is 0, and the rest are 1s. So it keeps everything else the same, while these will become 0 if you AND it together. And that's how I initialize it to 0. Because this will set the direction as 1, which will make it an output. But here I'm making it like an input to turn it off. And then right here, I just set a variable as index for going through the the string that I set as a global variable up here. And by doing that, I made a for loop that goes from 0, the start of the string, all the way to size, the size of the string that I set up here, minus 1, because arrays go from 0 to its size minus 1, for the same reason why decimal 0 to why we know that decimals have 10 values. So if we did like decimal and we said it was 10 values, and we showed that, and we listed each element in this array as the decimal, like 0, 1, 2, 3, we know that it goes from 0 to 9, right? Well, it's the same logic here. It goes from 0 to size minus 1 because this only goes from 0 to 9, right? Everything starts at 0. Very important concept. I think the only things that don't start at 0 is stuff I don't even want to think about. Anyways, so basically what this is doing is it's going through each individual character in this array of the string. Because this is the index 0, and it goes to this as a for loop, and every time it's incrementing that index. And it's setting conditions based on the index. So, for example, if we're at string 0, we should be at this capital C. And it says that if the string index is greater than or equal to a character, or it's less than or equal to a character, well, not or, it's actually and right here. And we use the double ands to set conditions. How do I explain this? This is different from this. This would set both of the values equal to no. This would set both of the values equal to each other. Like, it's used for initialization, like in this case. But this is comparing the two values. Are they equivalent? Well, if they're equivalent, then do this. That is the relationship that is happening right here with the ands. Two ands means that if this and this happens, well, you're gonna do whatever's under here. And since there's only one element, I don't use the brackets. Meaning this if statement only applies to this read, which is the function that is specified up here. Now, the way this works is that I set the character A and C, and since they're all in like an order in a C, I know that this range only applies to the lowercase values of the alphabet, and this only applies to the uppercase values of the alphabet. This only applies to the numbers, and this, well, it only applies to a space. So what I did was that for here, if it's corresponding to the lowercase letters of the alphabet, I subtract the character value. In this read, remember, it's an integer. This is the row index. So the result that's happening here is going to be an integer, seen as an integer. And let's say this is A. Like, what if the string at the very first value, index 0, was the letter A, lowercase? Well, the lowercase a minus a lowercase a is what? Well, anything minus the self is 0. And that's exactly what I wanted. Because what I'm doing with this row index is I'm using it for a Morse code array. I'm using this for another array. And I'll show you this array right now. Here. This is my Morse code array. And this is a two-dimensional array with 36 elements with a maximum of 6 elements. Now what I did was that a 0 represents a dot, while a 1 represents a line. And I make that clear through here. If the right here, the Morse code ends up being a 0, it's a dot. If the Morse code ends up being a 1, it's a dash. See? What this number actually represents, right here, is how far it's going to go. So, right here, I say that mj of 0 is the upper bound. So it goes from 1, which, remember, it starts at 0, so it's actually not even going to look at this number 2. It's only going to look here. It goes from 1 to 2. Why? Because mj of 0, and if j is 0 because of this value, then mj of 0 is 2. So it goes from 1 to 2. And it does these values. These conditions. These conditions. This whole entire condition right here is the for loop. I mean, not the whole entire condition. The whole entire, all these commands. This is the condition. So going back here, what I did was I basically assigned them to these rows. Like this would be 0. This is like row 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, blah blah blah, all the way down to 26 because there's 26 letters in the alphabet. 27, 28, 29, 30, and it keeps on going. So what I wanted to do was I wanted to map the alphabet to each other. And and I actually set the alphabet first, the alphabet Morse code first, because of this specific trait right here. If it's a lowercase letter, I wanted it to map to 0. But even if it was an uppercase letter, I also wanted it to map to 0 if it was an uppercase A. So that the Morse code would be the same. Like, if it was a lowercase a or an uppercase A, it would still do the same Morse code. And I think that's important because I don't want, like, an uppercase letter just to have an error for no reason. Like, an uppercase letter and a lowercase letter is supposed to do the same Morse code. So, the way this works is that it subtracts the value of the letter, like the lowest bound, so that it appropriately places whatever the character is into this 2D array. So if it was B, the character for B minus the character for A would be 1. because B is only one unit above A. So that makes it this value. And that's how this is working right here. Now right here, for the numbers, what I did was I did the same exact logic of subtracting the lower bound, but then I added back the 26 because, as you can see, add the former 26 letters to map to the numbers. Because there's 26 letters before this. I can't map it to 0 because in 0, for the Morse code, is the letter A. It's like the code for the letter A. I can't do that. I have to skip the letters in the alphabet to get all the way to the numbers. And then, right here, I made a space. I was thinking of doing a space inside the Morse code, but then I decided against it because the timing is different for the space character. It's kind of like a dash, but instead of being on, it's off. And that's kind of weird for it's kind of weird for me to like just put a whole nother thing just to make a space character. It's only one space character, so I can assign the code right here. That's precisely why I did it. And yes, this is the delay. And if you're wondering, right here, I kind of split it apart. Now, initially, I had the I as an int, but I decided to change it to an unsigned int because this MSP430G2 model, what you should really know about it is that it's known to be a low power MCU, meaning it's very cheap. It's supposed to be cheap, very cheap, very cheap. Especially this model, the G2, the G2 model. Like, there's other ones that have more capability, so they can be a little bit more expensive. But this G2 microcontroller is made to be the cheapest thing, which is why I use it as the coarse microcontroller. And the reason why I'm going on and on about how cheap it is because it means that the integer is pretty small. It's like it's not using a large integer. The largest size the integer can go is from negative 32,000 something to 32,000 something. And guess what? This is 30,000. So if I added these two together, then it would be 40,000, and it would go beyond the range, which would create overflow, and which will cause me to have like a value that I didn't even want. That's no bueno. I can technically combine these now that it's an unsigned int, but well, it is clearer this way because every single operation is supposed to have a 1 delay for the light being off for the next dot and dash. That's why I made it like this. Because literally, if you look right here, there's 1 delay for the next dot and dash, 1 delay for the next dot and dash, 1 delay for the next dot and dash. And I already explained the error checking, so that's fine. Now, I briefly glossed over this, but this is how my read function works. I used a read function in the first place because, one, this is pretty fucking complicated. Really, really complicated. And I needed to simplify it somehow. So, instead of like copying and pasting code and writing all these things multiple times, I decided to just make a function with this Morse code in it. And I threw in this two-dimensional array. Now this two-dimensional array was a cause for a huge stress for me when I first started this project. And that's because when I started this project, I actually had this two-dimensional array as a global variable. Big, big, big mistake. No bueno. No global variable. Because what happened, I think, is that because I had multiple functions, like the main function and the read function, it multiplied itself 2 times for no reason. No reason at all. And this thing's cheap, as I said. It has very low memory. And as such, I kept on getting memory errors. And I didn't know why. Until I realized it's a global variable. It's not supposed to be a global variable. Now there is admittedly other ways I could use to save space. Like I could have used malloc, which is memory allocation. But I think it's fine for this case because this is only using, like, the main purpose of this is just the Morse code, and I think it's even beneficial for it to be all clumped together because what a two-dimensional array and arrays in general they do is that they clump everything together, and by clumping everything together, it's much easier to access by the computer. Like, it's not in totally different places, so for some reason, like, you're going 2 miles away to get to like add 1 plus 1. Like, it's supposed to be right next to each other to have the similar speeds. You know, can't have the weakest link dragging you down. So I think the two-dimensional array is actually pretty appropriate for this. But the way it works is, as I said, this this first number represents how many units there are, meaning how far it should go. And the reason why I have the number at all is because this is a two-dimensional array of six columns for each of these whatchamacallits, these rows. Row, 5 to the power. Anyways, that means that I don't want to be reading past these two. I want to know when to stop. And the way I indicated when to stop is by using this initial number. And it's actually pretty convenient because it flows pretty well into this these for loops. So I use the first value of these characters in the for loop, and I created a k index. Yes, this is an index for the columns, and this is how it's gonna work right here. These, in the main function, the purpose is to find a character, and this character will dictate what the row index is. And once it's found the row index, it will go to that row index, and now it will use this k index and run through from 1, which is skipping the first value, which is 0, to the number that's in the first value, which represents the size of the actual size of the row, because some of these rows just aren't even size 6, you know? Like this is size 5, and this is size 4, because of course the initial element is included in it, so even though it says the number 5, it does have 6 elements because 5 is one of the elements. But the Morse code does have a maximum of only 5 dots or dashes. And that's for the actual decimals right here. So what I did was I made it loop through all of these columns for whenever it found one character. So it finds one character, it goes through here. Once it's found its row, it goes here. It uses this 4 as the maximum, and it goes 1, which is here, and looks at it. It's 1, right? So it says, well, if it's 0, then it'll be here, but it's not 0, so this doesn't happen. Else, if it's 1, then it does this, and it is 1. So it goes here, and it turns the LED 1 on, the red LED. There's a 3 times delay on the light, because it's supposed to be a long light. And then there's a 1 delay, and then it turns off right here with the FE, because this would be a string of 1s on the higher end, and this would be a string of 1s except for bit 0, which would be 0. And then there's a 1 delay for while it's off. And then, once it's all said and done, there's another delay. Actually, no. This is I think this should be character. Yeah, there we go. Once it's all said and done, there's going to be a delay to reach the next character of the string. Because there has to be a delay to tell you whence a character is finished. So you know what the next character is, you know the difference. And then it keeps on looping. It goes to the next index, sees the next one, and that's essentially how it works. It uses a toggle. I used a toggle here to exemplify. Well, it could be exactly the same. And this, it explicitly turns it off. It turns it on, turns it off, turns it on, toggles it off. Same stuff. And this is an empty loop, by the way. And I'm not sure exactly why we decided to use it this way, but due to the fortunately, at least since I'm being consistent, even though I don't know how long exactly 10,000 iterations is, I do know that at least that this is 3 times longer than this, because it's literally 3 times the value. And this is pretty much all the context I have to give you. Now, I know I spent quite a lot of time like explaining the logic and stuff like that, but hey, no one else is gonna explain it. If you want to like do this, like when you're doing this project on your own, I'd imagine that, well, you don't know what the heck you're doing at all, and those things, they are pretty dang important. So I suggest you, if you don't know about the logical things, just remember these key relations right here, because this will help you figure out exactly why this code works. And again, remember, this is all C programming, so you need to have very, very good knowledge and understanding of how C programming works in order to get it done. Well, that's all. Good luck on making your own Morse code.